You clicked on this video because you heard about the TanStack NPM supply chain compromise, and you need to know the real stakes. The truth is far more disturbing than a single bad actor. A compromised maintainer account can bypass every lockfile and CI check you trust, injecting malicious code directly into your production environment without triggering a single alert. By the end of this explanation, you will understand why your current security model is fundamentally broken and discover a zero-trust build architecture that forces every dependency to prove its identity at the exact moment it runs. Let us look at the events of March and May in 2026, when the NPM ecosystem suffered two devastating blows. The Axios library, used by hundreds of millions of applications, was compromised by the BlueNoroff group. They did not hack a server or exploit a zero-day vulnerability in the package manager itself. Instead, they targeted the human element. They stole the credentials of a legitimate maintainer, a person with full trust and access. Because this account was verified and trusted by the NPM registry, the malicious update was accepted as legitimate. The attackers injected a dropper called plain crypto.js into a package with 83 million weekly downloads. This single action bypassed all standard integrity checks because the digital signature was valid. The system did exactly what it was designed to do. It trusted the publisher. Here is the thing that keeps security teams awake at night. Your entire CI pipeline and your immutable release setup are built on a foundation of static trust. You assume that if a package passes the build, it is safe. You assume that a lock file guarantees the binary you are shipping is the code you reviewed. The TanStack and Axios incidents prove that this assumption is a dangerous illusion. When a maintainer account is compromised through social engineering or credential theft, the attacker becomes the publisher. They can push updates that pass every pre-deployment static analysis because the updates are signed by a trusted identity. The binary executing in your production environment becomes functionally indistinguishable from the source code you reviewed, even though it contains hidden malicious logic designed to exfiltrate environment variables or perform brand squatting attacks. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Reputation is not a security control. Even high-reputation libraries like TanStack are vulnerable to the same patterns as obscure packages. The attack vector does not care how popular a library is. It cares about access. If an attacker can get into the maintainer's environment, they can rewrite the history of the repository or push a new version that looks identical to the previous one but contains a hidden payload. This means that relying on the NPM trusted publisher model creates a single point of failure. If that point breaks, the entire trust chain collapses. You cannot fix this by updating your lock files or running more rigorous pre-deployment scans, because the scans will see what the attacker wants them to see. So, what is the solution? We need to shift from a mindset of trust but verify at build time to one of never trust, always verify at runtime. This is the core of the zero-trust build architecture. Instead of assuming a package is safe once it is installed, we must treat every dependency as potentially hostile until it proves its identity at the exact moment of execution. This requires a fundamental change in how we architect our applications. We cannot rely on the package manager to do the heavy lifting. We need an agent-based or sidecar architecture that sits between your application and the loaded modules. Imagine a security guard standing at the door of every room in your application. Before any code is allowed to run, this guard checks the cryptographic signature and hash of the module against a known good root of trust. If the signature does not match the current verified state, the execution is blocked immediately. This means that even if an attacker pushes a malicious update to the registry, the malicious code cannot execute in your environment because it fails the runtime verification. The attacker might have updated the registry, but they cannot update the runtime state of your application without the cryptographic keys that your zero-trust system holds. Now consider the trade-offs. Implementing this architecture introduces significant production costs. Every dependency must be cryptographically re-verified at runtime. This adds latency to your application startup and potentially to your execution paths. There is a computational overhead to validating every single module before it runs. For some high-frequency trading systems or latency-sensitive applications, this might be a deal breaker. You must weigh the security benefits against the performance penalties. The industry currently lacks real-world benchmark data on the feasibility of runtime re-verification at scale. We do not yet know if we can adopt such rigorous standards without fragmenting the developer experience or causing unacceptable slowdowns. The lack of data complicates the narrative. We know the vulnerability is real. We know the attack vectors are effective. But we do not know if the industry can sustain the overhead required to fix it. If every team has to implement their own custom runtime verification, we risk creating a fragmented ecosystem where security is inconsistent. Some teams might adopt the zero-trust build, while others continue to rely on static trust models, leaving the latter as easy targets. The question is not just technical, it is organizational. Do we have the collective will to accept the performance hit for the sake of security? The answer lies in the future of software engineering. We must accept that the current model is insufficient. The days of trusting a package because it has a green checkmark or a verified badge are over. We must build systems that assume compromise is inevitable and design our defenses to contain the blast radius. This means moving away from the idea that a build is a one-time event and toward the idea that security is a continuous process. Every time a module is loaded, it must be re-verified. This is the only viable defense against supply chain attacks that bypass static analysis. We are standing at a crossroads. We can continue to rely on the fragile trust models that led to the TanStack and Axios breaches, or we can embrace the harder path of zero-trust build. The latter requires more work, more complexity, and more performance overhead, but it is the only path that offers genuine protection against the systemic fragility of the NPM ecosystem. The goal is not to stop developers from using libraries. The goal is to ensure that when they do, the libraries behave exactly as they are supposed to, regardless of what happens upstream. This shift changes how we think about software delivery. It moves the burden of proof from the registry to the runtime. It forces us to confront the reality that no amount of static analysis can protect us from a compromised maintainer. The only way to win this game is to stop trusting and start verifying. Every single time. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.